Alrighty, cool. Let's give it a go. I think so. I did it last week and it didn't record my voice. I'll put that around here. That'll record you. But you asking all the tricky questions. I don't want that. Okay, so, I mean, this is page 21 in the notes, really. Conservation of energy. Newtonian stuff, this is all totally classical. Okay, we're going to have conservation of energy. We get, basically, the kinetic energy is equal to a half mv squared. Right, third year physics, right, we're quite happy with that, alright, so that's okay. Conservation of energy, we also need to add in our gravitational potential term, okay, which I have in the notes. So this is a kinetic energy because the energy depends on velocity, okay, it depends on how fast the objects are moving. That's kind of what we mean by kinetic energy, okay. Potential energy here is just a function of position. It doesn't matter about how fast the object's moving, its orientation or anything, it's simply where it is in space. Kinetic energy is just a function of r, of position, okay. And so this is equal to, in fact let me do this as, you be careful, so m2, what I'll do, you hate it when I do this, go back and change my notes, don't you, I'm sorry. So I'm going to try and use big M's consistently for mass measured in kilograms, little m's for mass measured in relativistic units. M2 is going to be, that's going to be my M1 in the middle, and we've got some much smaller test mass M2 orbiting around it. Okay, so that's the kind of situation. So we've got a satellite of M2 orbiting a central mass actually of just a big capital M. Okay. The gravitational potential energy between them is going to be minus G big M, big M2 divided by R. Okay, so that's they're the two energy terms. Okay, so kinetic energy and potential energy. This one here, okay, this velocity term, we can actually, so if we did conservation of energy, I'm just going to say that the total energy is equal to the sum of these two, right, which we've got here, so basically a half m2 v squared, and by v we mean the total velocity of this satellite, of this object, okay, minus g m2 divided by r. So v, depends on which direction this thing's moving, and v could be any particular direction depending on if it's going in a circle. It could just be falling straight inwards, it could be moving anywhere, because that v could be any direction. Given that we're kind of looking like we're going to be using circular polar coordinates, it makes sense to express that velocity in terms of a radial component and a sort of tangential component. Okay, so how fast is it going around and how fast is it moving in and out? Okay, so this would therefore become a half m2, if I just draw this out again here, right? So that's my m2 there. We're going to have a velocity kind of in the theta direction and a velocity there in the r direction. Okay, so any velocity it's got is made up of those two components. Okay, so half m2, so you could think of this as being v r squared plus v in the theta direction squared. Okay, that's just that kinetic energy term. And so if it has some velocity which happened to be like this, that would be some of this and some of this, and so the the v squared is equal to that squared plus that squared, just through Pythagoras really. Vr is simply equal to r dot. Okay, so how fast it's moving in the r direction is just dr dt. Okay, so this is simply, Vr is simply r dot, so that becomes the r dot squared term. If you look at the notes, we have an r dot squared term in there too. V theta is not quite theta dot. Okay, so theta dot is going to be a variation in angle. The velocity in the theta direction is going to be equal to r multiplied by theta dot. Okay, so if we combine all that together, we basically end up with the total energy is going to be a half m2 r dot squared plus a half m2, so v theta squared is going to be r squared theta dot squared, r squared theta dot squared minus g m2 divided by r, which I think is equation 1 in my notes. A half m2 r dot squared plus a half m2 r theta dot squared minus g m2 over r. Okay, alright, good. Hopefully that's all alright so far. It's kind of, yes sir.
A diagram.
Oh yes, the diagram, yeah.
which is the planet and which is the sun?
Ah, right. This big one here is the sun, with the light coming out of it.
We've got it moving as well.
No, that one's stationed, and I've drawn two masses because I ran out of space for that satellite. And this is yeah. Sorry, I've got to work on my drawings, haven't I? Is that what you're saying? This is the star in the middle. This is the test mass, but I then ran out of space to carry on my drawing, so I redrew it down here with a bit more space around it, and did it in pen. and couldn't rub it out. And yeah. Note to self: become an artist. Is that all right, Desmond? Are you confused still? This is the central mass.
The V velocity.
Yeah.
Just the V. Is that your resultant one?
It's a resultant velocity.
Is your VR going outwards in that diagram that way?
It would be, because if that's my radius vector, an increase in r is going that way, right?
Should the V be within the axis of VR?
It's just got a negative VR component.
Okay.
But you're right. I mean, it's some. Yeah. VR is a thing going this direction. If VR was negative, this here is a negative value of VR. Yeah. So far we've kind of done conservation of energy, and we've used Newton's gravitational potential energy as well. Another thing we're going to throw in, we know that in this system there's going to be conservation of angular momentum. Okay, we're assuming a big central mass, so basically the angular momentum of the satellite orbiting is going to be conserved. So we can write the angular momentum. So the way I've done it in the notes, let me just see how have I done it. Yeah, so the angular momentum L is basically equal to the mass of this object multiplied by r squared theta dot mr squared omega is the equation for angular momentum, okay, or m v squared over r, which is, so this is the equation for angular momentum. But let me actually define a slightly different one. So little l is equal to big L angular momentum divided by unit mass. Doesn't make an awful lot of difference, to be honest. Let me have a look what did I swap? Yeah, you're right. The notes I'm using phi, aren't I? So, what do you want?
That should be theta.
We'll go back to theta there, shall we? Although it's angular momentum. Angular momentum normalised by the mass of that object. So, just dividing through. It's big L divided by m2. Yeah, okay, so this is my little l, which is therefore equal to m2 r squared theta dot divided by m2. So this little l is equal to r squared theta dot. So from here I can go theta dot is equal to l over r squared. And this is useful. Okay, this is simply conservation of angular momentum, but it lets me. So this was my kinetic energy term here, okay, and this was my potential energy. My kinetic energy term only depended on the velocity. Either how the first term, that r dot squared term, is how fast the satellite is approaching or moving away from the central mass. So that r dot speed. So whether they're getting nearer or further away, and the theta dot term is how fast it's moving, it's orbiting around it. Okay, so there are two velocity terms, two kinetic energy terms, and then this one here, which is a potential energy term. But the sneaky thing is, right, this here lets us convert from a theta dot of velocity into a position. Okay, so what we can do is we can substitute in here for theta dot, and basically then this term here, which looks like an angular kinetic energy, is actually going to only be dependent on position. Because if you're conserving angular momentum, the closer you get, the faster you move. As you move further out, you go slower. So there is a relationship between position of r and angular speed. Okay, and so as you change your radial position, your speed changes. Right? Classic conservation of angular momentum. But what it means is we can use this term to sub it in there. Okay, and so if we do that, we get total energy. I'm still on the page here. Total energy is equal to half m2 r dot squared plus a half m2 r squared. Now theta dot squared is going to be l squared divided by r to the fourth minus m2 over r. And now actually this bit here is a kinetic energy term, right? And these ones here both are only dependent on position. So they're kind of like potential energies, right? Even though this one we know is something to do with its angular speed, it actually, that term is only dependent on r. Okay, so we can simplify that. In fact, we're going to simplify it and also divide by m2. Okay, so we're going to get the total energy per unit mass of the orbiting object is equal to 1/2 r dot squared, and then this term here is going to be just checking what I get here. So that goes out with an r squared there. We're dividing through by m2, so this is going to be simply plus l squared over 2r squared minus gm over r. Okay, so that's our overall energy for this system, okay, where we have, this is a kinetic energy term for sure. A radial kinetic energy is how fast the object is moving away or moving towards the central mass. Our little test mass, our satellite, how fast that radial coordinate is changing, okay. So it's not its overall speed, but it's the speed of approach or moving away from the central object, okay. And this thing here we're going to call a potential energy effective, okay. So this is a classic, this is a normal potential energy, and this is a potential energy that somehow incorporates the use, this conservation of angular momentum in the radial direction, okay. So we end up with this thing here. So this bit here is the effective potential energy, okay. And we're going to basically, with the Schwarzschild solution, we're going to come up with an alternative equation like this with an extra term in the potential, the effective potential, okay. So I think in the notes I called it V sub f as a function of r. So this crucially is just a function of r, okay. So this term here is just a function of r, and this is our kinetic energy as before. I mean, this looks like a real mess to actually solve this, right? You go, oh, okay, well, how can we predict the different equations of motion from this? It looks tricky, but actually there's a really lovely graphical approach that we can, yeah. Yeah.
That would be big L squared over m2 squared, so we still have that effect.
So why does what cancel out? What was your initial?
The m2 in the energy term, the little L is basically equivalent to like big L over m2.
Yeah.
So wouldn't that mean that you have a big L squared over m2 squared instead of little L, which means you've got an m2. Yeah, but it wouldn't be little L anymore. You'd have an extra factor in there.
Well, little l is, so this is energy per unit mass of the orbiting mass, and this is angular momentum per unit mass of the orbiting mass. So we're kind of ignoring the effect. Is that what you mean? You mean this little l has an m2 hidden in it?
Yeah.
Yeah, but if let's just say little l is little l, right? And so it's angular momentum per unit mass of the orbiting satellite. In the same way that this equation is total energy per unit mass of the orbiting satellite. Set it equal to 1.
It doesn't really have it doesn't really have an m2 in it, because little l is big L divided by m2, and then on the same basis as subjects in it, big L has another m2 in it.
Well, yeah, I mean, exactly.
Anyway.
Yeah, I mean, think of little l as the angular speed multiplied by the radius squared, right? I mean, those are two completely non-mass dependent objects, really. But I see what you mean. Have I really hidden the mass? But effectively, this thing is really independent of the mass of the. I mean, you know that the mass of a test mass is independent of its mass, right? It doesn't matter how it orbits; it's the same. You know, if you had the moon or a pea or whatever you want to put into orbit at the same position near the sun, they're going to move the same. It doesn't matter what their mass is. So physically, you hope that the m2 doesn't really make any difference. So actually solving this equation is a little bit tricky. You have to do this thing called Binet's equation and stuff, which we won't go into. But what we will do is this is an effective potential, right? It's a potential energy. And you can plot a potential energy. Hooke's law gives you a parabolic potential energy, and you put an object in there and it'll kind of oscillate backwards and forwards, and you get simple harmonic motion, right? If you do the potential energy for a spring, F equals minus kx gives you a potential which is a half kx squared. So this is kind of the effective potential of a spring, and so therefore if you have a known total energy in your system and your object starts here at rest with 0 kinetic energy, all of its energy is used up by potential, effectively it'll kind of slosh backwards and forwards in this basin. When it's at the bottom here, it will have maximum kinetic energy, zero potential energy, and it'll come back up the other side. That's basically just a spring oscillating backwards and forwards, right? Or even think about it gravitationally, it's a ball rolling backwards and forwards in a well. But if you plot the potential energy like this, okay, you can start to predict some of the equations of motion. Right? From this you can't tell it's going to be simple harmonic motion, but you know if it's got a certain energy, it'll only ever slosh up the other side as high as you released it from, and you can see where it's going to be moving its fastest. You can learn some stuff about its equation, about how it moves, by simply plotting the effective potential and saying this is how much energy I've given it to start with. Okay. So we're going to do just the same thing. We're going to plot this thing out and see what we get for the Newtonian case. Let me actually